Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And what I have for you today is yet another iteration of a conversation around strong types versus weak types. This is more of something that I found out, that I thought about while listening to more and trying to understand how strong type proponents think, and I realized one interesting thing. I think they have a blind spot, and this is absolutely expected because every school of design has its own blind spots. But I think I finally put my finger on what that blind spot is. And I believe that that blind spot is related to language and more focus on the math part of programming than on the language part of programming. Okay, so let me try to explain this. First of all, let's set some context here. This is an older article from 15 December 2020. To the brain, reading computer code is not the same as reading language, but what's interesting is that it's not the same as reading math either. So it seems from this, if you're reading through this, is that understanding computer code seems to be its own thing. It's not the same as language, and it's not the same as math and logic. And basically, this research shows that what we need to do is we need to think about programming as its own thing, but it's something that is somewhere between math and logic. And actually, another article that I've read points out that these areas that they are talking about, the required learning. So they are talking about areas in the brain, the general purpose brain network. These are areas that are fundamental to more types of operations and that tend to be involved in a bit in math, a bit in language or writing. Okay. So what this tells me, I mean, I have a strong intuition. I've always had a strong intuition that that programming is somewhere in the middle between writing and mathematics. And perhaps it's something that's more fundamental to it, and that I cannot fully express because we don't fully understand it yet. It might be something that's kind of the fundamental of math plus fundamentals of writing, and it becomes its own thing. Because what we are doing as programmers, and by the way, this was mostly about understanding code, it was less about writing code. But what we do as programmers is often create concepts, and those concepts, you can see them in two different ways. One way is that they are a semantic network very similar to a jargon. And the other one, so this would be the, let's say, language side. The other side, the other way we can look at it is that it's a collection of mathematical constructs that we build and that connect to each other. So basically, one way that I've heard it described when you're using strong types is that you'll have each function that you write on a strong type is a theorem for that type that proves the type. And this is an old-time equivalency in mathematics, actually. So we have these two different domains, the domain of language, the domain of math. So now what happens when you take people who are very focused on math and they want to build programs? Well, I think it's natural to assume that they will look at building mathematical structures, formal systems. And those formal systems are mainly types. So let's look a bit at what Martin Odersky is talking about. So in case you don't know, he is the lead designer, if I'm not mistaken. Anyway, he's one of the most important people in Scala language design, if not the most. And I finally watched one of his talks, very interesting talk about, it's called The Problem with Types. I was more interested in the first half because it's talking about the differences between static and dynamic and how he sees the world, basically, in terms of language design and type systems. But then the second half it was more about implementations in Scala, which for me it wasn't that interesting. And it's an older conference, but the talk is still very, very interesting, very actual. So he talks about the difference between static and dynamic. And actually, let me show you this in the slides here, because there's types, everyone has an opinion of them. In the industry, it used to be the norm to have types, and today split about evenly between static and dynamic. So we have these languages like Ruby, Python, JavaScript, who tend to be more dynamic. In academia, static types are more common, which makes sense if you think that academia is more of a math-focused, science-focused. It makes sense that they will go with the more, what they believe is the more structured approach, which is static types. And you will notice that I don't fully agree with this, but I want to be very clear on why. So please bear with me. Okay, and then he talks about how static languages have a few points in favor. They are more efficient, better tooling, fewer tests needed. I disagree with this based on my own experience. But this is the first thing that shows me that they have a blind spot for something very important in programming, in design. Naming. And I will go back to it in a little bit. Better documentation, more or less. I mean, if you write tests as a text, then you'll have better documentation anyway. So, more or less, I don't fully agree with this. Safety net for maintenance, not quite. Okay. Dynamic, what I say, simpler languages, fewer puzzling compiler errors, no boilerplate, easier for exploration. But what I find the most important part, no type imposed limits to expressiveness. From my point of view, dynamic languages have won for me because I can express what I want in the language without being encumbered by and having to write a lot of things for the compiler. I feel whenever I'm using strongly typed languages, statically typed languages, that I have to do the work of a lot of work, or some work for the compiler, instead of doing the work for me or for the next programmer and for the problem that I'm trying to solve. Okay, so two different views. And then he goes into talking about what is good design. Clear, I agree with this. Correct, yes. But there are different ways of obtaining correctness. One of that is tests and test-driven development. One of it is through guidelines, constraints, code reviews. And another one is through strong types. And then the next one, minimal. Yes, fully agree. The opposite of random. I like this very much. Indeed, good design, it needs to be intentional. You need to look at it and feel the intention, feel the intent. I did a full talk about design intent and how to express intent through code a few years ago. It is one of the most important parts of design, if not, let's say, the most important. Because if you have intent, this is the opposite of random. In any other design discipline, is called intent. If you have intent and it permeates the whole design, everything else will fall into place. Because with intent, you have correctness, you have clear, you have minimal. If you don't have intent, the rest are needed. you need these as constraints. And I also like that he's talking about great designs are often discovered, not invented. Absolutely, which is one of the reasons I love test-driven development, is because I don't make any assumptions about the design, but instead I build step by step, little by little, and I discover the design. It's a discovery process rather than a invention process, let's say. Good. And then he goes and talks about the elements of great design. So we need two things, patterns and constraints. And I agree, we need patterns because patterns help us understand the code better and solve the same problem in the same way. And constraints. Yeah. But here is where I don't agree with him. Patterns turn into abstractions, which is correct up to a point, in the sense, I mean, by abstractions, he talked a bit about object-oriented, but it's not really what it is, because patterns are just solutions to problems. Same solution to same problem in the same context. This is what a pattern is. And that's how we should see it. And it might lead to abstractions, but not necessarily. Okay. Where I don't agree at all is that the constraints turn into types. Types are not the only form of constraints. Tests are another form of constraints. And also, very important, individual constraints, things that we set upon ourselves as constraints, are also part of the design process. For example, test-driven development, it's a discipline. It's a constraint that you set up on yourself in order to design software. Could you design software in other ways? Absolutely, right? But if with this constraint, it can help you design software. Okay, so that's fundamentally where I disagree. He sees constraints only as types, whereas I see constraints as being naming, for example, using only names from the domain, only very clear names, and so on. So, and then he goes and makes a classification of type systems so that we know what we are talking about. We have weak dynamic, strong dynamic, weak static, strong static. And down here we have weak dynamic assembly. And then we kind of have strong types and dynamic Python enclosure, which is true. So in Python I have types, but I'm using them behind the scenes. I don't use them as the most important part of my code. Instead, I focus on things that solve problems rather than on building types. And on top, Java and C# are somewhere in the middle. C++ could probably be anywhere here, depending on how you use it. It can be, well, maybe not weak dynamic, but it can be in a lot of places around here, depending on how you use it. Scala tends to be here, Haskell and OCaml here. So OCaml and Haskell, very static, very strong typed. You need to use types for everything. So on. All right. So then he goes into talking about another classification, which is weak, strong, and then coarse versus detailed. And strong and coarse are Java 4 and Go, which is my way or the highway. Basically, you have a few types. You cannot build a lot more types easily. Well, you could build classes here, but when it talks about types, it doesn't talk about classes. This is a difference in when you think about it in terms of functional programming. Types are not necessarily classes. And then here we have weak and detailed, like Eiffel, TypeScript, Dart, C# in Java 5+ here. And then you have strong and detailed Scala, F#, Haskell, or OCaml, where everything is typed to the max. So, and he's talking about one thing. I'm not going to insist on this part because I didn't find it that useful or interesting, but I found the example a bit weird. So basically what he's saying is that he's talking about a problem with types where you have a generic type. Let's say you have a list of employees, and then you want to apply something that, because an employee is a person, then anything that applies to a person should apply to an employee as well. And I can't help thinking that it's not how it works, because I would never model an employee as being a person. This is a very strong assumption that an employee is a person. What if the employee, is an external company? You're treating that. I mean, what if you will have AI as employees in the future? I mean, these are things that don't make a lot of sense to me. The notion of employee is not really an easy relation to a person. I think it should be connected to a person. But when we are talking about employees, we are typically talking about them in a very specific context. When we are talking about persons, we are talking in a different context. And these two things tend to be in different parts of our applications. So I don't see a reason for connecting them. But hey, this is a pet peeve, maybe. Maybe not so interesting. Okay, so after seeing this, let's go back to what I think is the problem. And I think the problem is that people find, so once again, math people who are focusing a lot on mathematics will start by building these type systems. And one thing that always has annoyed me about this is that those type systems, they tend to go into very abstract realms, and it's very, very difficult to understand how to use them. Okay? And I think that this shows that, in fact, they are having a blind spot about names. and the importance, the very, very important part, which is names in code. Let's take a little bit of an example. A few years ago, I did an experiment with a friend. We were at a meetup, and he was an expert in Haskell. And I told him, okay, let's use a web framework in Haskell. And Haskell is one of those very strongly typed names. It's one of those strongly typed languages. So let me also add a little bit else, because you have very strong typed ways of building software, which means you have ways of creating type systems for your product that will stop you from using any invalid state. Okay, so to give you some examples, let's say what you have is money, okay, but you know that you only have euros and the amount needs to be positive always. You never have negative money in your application. So you can create systems where if you pass in minus 20 euros or minus 20 USD, it will just give you a compile error, not a runtime error. Very important. So you'll get feedback not at runtime, but at compile time. Now, I've learned this a very long time ago from a book by Andrei Alexandrescu about C++. And in that book, he's proving how you can do these things with templates in C++. I'm very familiar with that. And intellectually, it's a very interesting exercise. If you've never done this before, by all means, I encourage you to try it out and figure out how you can create states that are, so create types that are only valid for the valid states of your application. And this is what I call very strong types, right? It's where you have using type system in such a way that you disallow any combination that is not available for your product. Now, of course, this comes with two problems. The first problem is, how do you know that you have figured out all the combinations for your product? You don't, and most likely somebody will come to you and say, oh, we actually need another currency or 10 other currencies, and so, or whatever else, other types of combination, or that thing which used to be a number now is a formula, or and so on. And with types, you can do some neat things in the sense that you can combine types. You can do kind of union things. Say, is this type or this type? So maybe it's a number or let's say it's the euro type, or is the USD euro currency type, or the USD money type, or whatever, all the types that you support, all the representing all the currencies that you support. You could also do a kind of intersections or a kind of inheritance, right? Add to this type a few other methods, and so on. Funny enough, I've never seen, and one thing that I'm missing is to say, I want all the methods from this type except these methods. So if you take, for example, the string class, in many languages, they have a lot of things in the string class. But what if I don't want to have any string operations? I just want a string representation. And no operations are allowed on my type. This could prove useful in various contexts. And one way to do that is by having a limited type that's just the representation, and then combine it with other types that have addition and equal and all the other operations. But maybe there should be the other way around, which is I want this type except these methods. So kind of extract methods. We always think about adding stuff to our types instead of doing doing it the other way around, constraining types. I'd like to have constrained types as well. But anyway, that's another story. So you have these kinds of types, okay? And the first challenge is you'll never know which are all the valid combinations in your software. And when a new combination will come, first thing you'll need to do is to understand what the existing type system is before you can add more options to it. And here is where things get messy, because usually these existing type systems, they tend to be very, very abstract. Even think about this. So we were talking about strings, string representation, and operations. How would you call the string representation type? Is it a list of characters? Is it a vector of cars like they used to do in C++ and they realized it's is not the best idea? You see there are, and then the vector still has some methods on it. You can still add things to the vector and so on. So maybe it should be something that is a constant vector, immutable vector of characters that completely disallows change and so on. How do we name that? And imagine you are using this to you're doing the same operation but on more complex types. You end up with a bunch of things, okay? And then if I look at this, so I was with my friend, we were saying, okay, let's use Haskell to build a web application. And the first reaction was shock, because apparently no Haskell programmer builds web applications. And the second reaction was, okay, let's look at some frameworks. And it took us quite a long time to figure out how to use it. And the reason was, and what I'm showing you here is Hapstack, which is a modern type-safe web development in Haskell. Sounds really good. Except I'm seeing this, RQ data. Okay, RQ probably request data. We use checkRQ. Let's look at checkRQ is a monad. Has RQ data, either string something. Okay, my Haskell is a bit rusty. Okay, so I don't fully understand all this, but one thing that I can focus on is names. Okay, monad, I know what a monad is. RQ data has RQ data, not that bad. Let's look at something else. We had somewhere XML Gen T. The XML Gen T, it's a monad transformer which takes an M and A. And you also have an unXML Gen T, which takes an XML Gen TMA. All right. So maybe you see where I'm coming at. I think that I found the thing that annoys me the most about strong type systems. And that thing is due to a blind spot of the people who are proposing strong type systems. And that blind spot comes from mathematics. How do we name things in mathematics? Well, we are very lazy. Like we call things x and y and z, because these are the coordinates, and o is the origin, and we need imaginary numbers. Fine, we'll use I, x plus y I, or a plus b I, and that's mathematics, right? And then how do we name theorems? Well, Pythagoras theorem. What does it tell you about the contents? Nothing. It tells you about the guy who presumably expressed it. But if I were to name things correctly in mathematics, I would name them completely differently. Like instead of x and y, probably I'll do horizontal and vertical. And z, I will have to find a good name for that. I don't have one at the moment, like depth, maybe. And then if I'm talking about Pythagoras theorem, how about the theorem of relationships between the sides of a straight triangle or straight angle triangle? I forget how it's called. Right? This is what I would expect as a programmer who is focused on naming. But if you come from math, you are used to those things, and then you are used to naming things in a very, very unexpressive way. Because as long as you understand it and you give it a definition, and other people can learn the definition, that's what math is. And I think this is the big blind spot of strong type system proponents. Naming. And it comes from the fact that they are using their math brain and completely forgot about the other part, which is the language brain. So how does my code look like when I'm using weak types? A few years ago, we're building a product, and we made the decision to use Grails, which is similar to Rails, but on top of Java, a JVM. And we also decided to use types only at the entry in the system. It was a web application, so only use types where you have the request is processed initially, because there we needed validations. And then to avoid using types in the rest of the system, inside of the system. Now, of course, for somebody who's doing type systems, this would sound like something that you should never do. I even heard that this is not moral and it's bad and so on. But I don't believe it is, because what happens when you have a function, but you don't have a lot of information about the parameters through types? It turns out that the natural thing to do as a programmer is to find better names for that function, better names for the parameters. And because you have better names for the parameters, instead of having things like S and T, you had start date, end date, so on. was there any type or client or user, or was there any time a problem with us not knowing what type we were supposed to pass in? No. We always knew what type to pass in. Our methods were very short. They were doing one thing. Moreover, we needed to, I expected that we'll need more tests to compensate for the fact that we didn't use types. That wasn't the case. We were actually just testing what the function was supposed to do. And at the edge of the system, testing for security and other weird things. But those were captured partially by types and partially by validators. Anyway, so we didn't need more tests. The code was very easy to understand. Because it was very easy to understand, it was very easy to change. And it allowed us to experiment. It allowed us to work less for the compiler and more for solving the problem. Now, do I believe this is the only way of developing software that makes sense? No. I believe that there are different ways of developing software that make sense for different contexts. But I think the most important thing here is to see where your blind spots are as a designer. And I would really love to see people who build strong type systems make a really good effort in introducing better names. Because despite what they believe that dynamic languages are, they believe that people are using dynamic languages because it's easier and so on. It's not. It's easier to understand things because the names are very clear because you don't have type information. And so you need to be very clear in other ways. And it becomes very clear by using names and certain conventions. So if I'm going back to the slide, let's see. This slide, patterns that turn into abstractions and constraints that turn into types. This is where I completely disagree. Patterns, yes, we could say they turn into abstractions. Constraints, we have different types of constraints. One of them is types, another one is naming, another one is tests, another one is things like test-driven development, which are constraints on how we build software. Right, so with this being said, I still have to add one more thing, which is common between the two approaches. So if you are thinking about how people are building software using strong type system versus how I would be building software using test-driven development, I think the process is very much the same. Okay? Because the process is the following. They create a type, they validate the type through a function, and this tells them that the type is correct. And then they add something more to the type, they add some more functions, and so on. So it's an iterative, exploratory process and a discovery process. And the way they are building correctness in is by using strong types. And they say probably we don't need tests because we have the strong types. And we are validating at compile time and so on. I have my doubts about that, but okay, let's assume that this works perfectly fine in this way. what I would do is I would think about the next behavior I need to implement and write a test and see the test fail, and then implement the code and refactor. And in refactoring, I discovered the design, and my constraint is not the types, but it's this process of writing a test, adding more things. But it's once again, both processes are incremental and are based on discovery. So we completely agree here. We are just using different building blocks, right? I am building based on behavior, taking a problem, splitting it into smaller problems in terms of behavior, and then solving each small problem one at a time. Whereas in the case of strong type systems, what you would do is take a behavior, figure out what the constructs are that you need, validate those constructs, validate them, and so on. So it makes sense. I think these both approaches make sense. But I don't think one is necessarily better than the other. With strong types, you have slower compile times, more difficult error messages to understand, a harder entry, higher barrier to entry because the type systems are complex. You need to understand a lot of abstractions before you can go into something like this. And from my point of view, a lot of work done for the compiler. A lot of work that I do for the compiler. While on the other hand, in my approach, what I have, or test-driven approach, what I would have is focus on behavior, clarity, a lot of naming, good names that allow me to get into the problem quickly, and correctness built in through tests, and not fundamentally no compile times, but I need to run the tests, and the tests can be very fast. At some point in the talk, Martin Odersky talks about how tests are too slow for feedback because they take 15 minutes or so. I disagree. I mean, we can run thousands of tests in seconds if we write them in an appropriate way, focused on behavior and not touching the outside world, which is basically what types are doing as well, because types will not touch the outside world. So, two different approaches. I don't think anyone is much better than the other. I have to add one thing though related to types, because when type systems become Turing complete, you get something more, which is, I think it's called the incompleteness theorem. When you have a Turing complete language, you cannot prove that a program is correct. Or there are programs that you cannot prove are correct, something like that. And this leads to potential security vulnerabilities. So you need to pay a lot of attention in general to when your programs become Turing complete, or the languages that you are using. Because, let's make no mistake here, what you're doing with type systems, you are basically creating a formal language. What I'm doing without type systems, or with weaker type systems, is I'm creating a jargon. Those two are kind of complementary, but similar. But on one hand, we focus on the formality of the system that makes it work. On the other hand, we focus on the people and understandability, and the combination, this combination of social and technical things that makes the whole system work and click. and these two work together. So anyway, pay attention if you get to Turing complete systems. You'll probably need some extra things to do for security. So, in conclusion, the short version, I believe there are two approaches to software design, two main approaches. One starts from mathematics and builds formal systems, and they have their advantages, but their blind spot is the power of language. And the other system focuses on language and on behavior, on construction, and we don't want to do the work for compilers. We want to do the work for solving our problem. And this approach, these two approaches can be equally correct. I don't believe when they are saying that their approach is the only one that leads to correctness. No. Both approaches can lead to correctness, probably to the same level of correctness, with their own caveats. But what is actually missing here, and the blind spot for strong type system proponents, is the power of language. And it's something that we need to take into account. And I think that in this job, you should take advantage either of the power of mathematics or of the power of language. Maybe we'll find a way to merge them at some point. But I think that most programmers don't take advantage of any of these things. They kind of try to make things work and fight instead of using any of these two superpowers in their favor. So if you take something from here, learn the power of mathematics, strong systems, learn the power of language, use at least one of them, because one of these is a superpower. Both of these are superpowers, but probably one of them will fit you and your team. And that's the one that will make your systems better. All right, this was it for today. What do you think about all this? Have you used strong types? Do you see the value in using formal systems? Do you see the value in using the power of language? Let us know in the comments. We love comments, and I can't wait to have more interesting conversations with you. Thank you kindly for the view, and until next time, remember to think, design, and work smart.